This is the surface of a geranium leaf. Here's a close-up. You can't take this kind of picture at home. You need one of these. Ordinary light microscopes, like you used in school, have a limit. At the microscopic level, light waves are bigger than some of the things we'd like to look at. The electron microscope shows us new worlds by using a stream of electrons to replace the light beam. This is a transmission electron microscope and functions much like a light microscope, except for the electron beam where the light bulb should be, and a fluorescent screen for viewing the result. Being a television crew, we gravitated quickly to this machine's cousin, the scanning electron microscope. The operation of the scanning electron microscope is easier to see, and the instrument is similar to a video camera in a lot of ways. So today, it's going to get the media coverage. Here's what's inside. At the top is an electron gun. A small heated filament emits electrons. A positively charged plate called the anode attracts those electrons. At the anode, the electrons get a surprise. There's a hole in it, and many of them slip right through. Since the stream of electrons will bend in a magnetic field, circular electromagnets focus the flood into a tiny spot. The focusing magnets act like lenses on the beam, and they're called lenses. At the bottom of the unit is the stage for the specimen. The scanning electron microscope looks at the surface of things. To ensure a path for excess electrons, the specimen usually has to be plated with a fine coating of metal. Wherever the beam lands, it excites the specimen to give off electrons of its own. Depending on the angle of the surface of the specimen, varying amounts of these secondary electrons are attracted towards the collector. Some electrons pass right through the collector and land on the scintillator. When electrons strike the scintillator, it gives off light, just like the picture tube you're looking at right now. The light is piped to a photomultiplier tube. The photomultiplier converts the light back into electrons, then uses the secondary electron phenomenon to amplify the signal. So, where's the picture? The amount of signal at the output of the photomultiplier is proportional to the number of electrons collected at the scintillator. The number of electrons collected at the scintillator depends on the surface of the specimen and where the electron beam hits it. This thing isn't called the scanning electron microscope for nothing. Another set of electromagnets in the beam's path deflects it left to right and up and down. As the beam scans the specimen, the output signal changes strength. This signal is then displayed on a cathode ray tube, a picture tube to you, using the same scanning pattern. The interior of the microscope is at vacuum to avoid the electron beam crashing into air molecules, so the specimen has to be installed through an airlock, like a spaceship. In this case, the specimen is an air-dried, gold palladium-plated dog flea. The control panel allows the adjustment of the electron gun's emission, the beam's accelerating potential, the focusing of the electromagnetic lenses, and the scanning size and speed. As the scan size gets smaller, the amount of magnification increases. The scanning speed controls how clear the image will be. If the same line of the specimen is scanned multiple times, the signal is clearer. High-quality photographs can be taken by slowing the scan way down and using a piece of film to record the image. This is a photo of a microchip. Here's the tick that's responsible for Lyme disease. You think it's ugly now. Here's its mouth parts. On second thought, maybe it's a good thing we don't have one of these at home.